So just before the break, we returned back to this problem of this arrangement of atoms. This functional group, you're going to learn about functional groups in like tomorrow, but this type of arrangement with a doubly bonded oxygen and an adjacent nitrogen is called an amide. And I told you, you're not surprised by the fact that the carbon and the oxygen that are doubly bonded to each other are sp2 hybridized, but you were surprised that the nitrogen was sp2 hybridized. Because looking at that nitrogen, you would say, hey, wait a minute. The nitrogen's surrounded by 4 groups and should therefore be tetrahedral and sp3 hybridized. The thing that makes it not sp3 hybridized is the fact that lone pairs are adjacent to a pi bond. And when this happens, you can do the same resonance 2-step that we did above. That screen needs to come down a little bit more, doesn't it? There we go. We can do the same resonance 2-step that we did before. We take the lone pair that's adjacent to the pi bond, we move it over to form a new pi bond with the atom that was previously participating in the pi bond. Then we take the electrons in that pi bond and move them up onto the oxygen. Then we draw this doubly headed arrow here. This arrow, doubly headed arrow, communicates that these are resonance structures and that they are both valid descriptors of the same molecule, and that they are not actually in equilibrium with each other. They are not hopping back and forth, that both of them represent the molecule simultaneously. If we draw the new resonance structure, the electrons that used to be a pi bond between carbon and oxygen should now be a lone pair on oxygen. And what should the formal charge of that oxygen be? Got to be negative, right? How about, and then the lone pairs that used to be the lone pair on the nitrogen are now in this nitrogen carbon pi bond. What should the formal charge on the nitrogen be? Has to be plus. Have we broken any rules? We haven't broken the octet rule. Our formal charges are correct. Is the total formal charge the same in each resonance structure? You bet. So these are both correct. Now remember the implications of resonance. They're both valid descriptors of the same molecule. We rearrange electrons. We do not rearrange or move atoms. The molecule isn't moving. The overall formal charge is the same, but both resonance structures contribute to the actual properties of the molecule. If we were to draw what we expect the structure of this molecule to be, we would put a delta minus on the oxygen, and we would put a delta plus on the nitrogen, and we would say that we expect there to be partial double bond character between both the carbon and oxygen and the carbon and the nitrogen. That's what we would expect the hybrid structure to be. Now, there's an interesting implication to this one. We do not move atoms. Tell me what sp3 hybridization means in terms of shape. If an atom was sp3 hybridized, if a nitrogen was sp3 hybridized, what would its geometry be? Basically tetrahedral. You'd have one lone pair occupying one of the spots, and then it would look like this. And let's just put a couple of R groups on there to just be, so this is an example of a sp3 nitrogen. If a nitrogen instead were sp2, what would it look like? Would have to be trigonal planar. We would draw that maybe like this. You'd have to imagine looking at something that's flat on the edge, and the bond angles would all be 120 degrees. And here you'd say that the lone pair was in an sp3 orbital. Here you'd say that the lone pair is in what kind of orbital? Has to be in the p orbital, right? Because you've accounted for the sp2 orbitals here. This is an sp2 hybridized nitrogen. Do you see how the geometry changes? Do you see how in sp2, 3 hybridization, the nitrogen's like this, and then in sp2, it flattens out like this? So changing hybridization from one resonance structure to the other would be the same as changing geometry. Yes?
So for it to be like this sp2 hybridization, one of these R groups you would have to assume has a pi bond.
Yes, that's true. For it to exist here, one of these R groups would need to be, for it to be this way, one of the R groups would need to be what we've drawn above. My point is that in resonance structures, because you are not allowed to move the atoms, you can't change hybridization. Okay? So that's important point 1 for understanding why the nitrogen's sp2 hybridized. In resonance structure, you can't change from sp2 back and forth to sp3. It has to be one or the other. That involves, doing so would involve moving atoms, and that's a big no-no. Okay? The second thing is that resonance delocalization is stabilizing. In order for the lone pairs on that nitrogen to participate in resonance, the nitrogen has to be sp2 hybridized, so the lone pairs can be in a p orbital where they can line up with side-by-side overlap with the pi bond of the carbon-oxygen double bond. Okay, so the third observation is the lone pairs must be in a p orbital to overlap side by side with the pi bond. And you've learned about pi bonding orbitals last time. Just to refresh your memory, what does a pi bond look like? Here we're looking at a carbon-carbon pi bond from the side, and I drew what that looks for you here, above the plane of the carbons and below the plane of the carbons. If this were a nitrogen and had a lone pair on it, the only way that lone pair could align with the pi bond is if the lone pair were in a p orbital. And I'll actually draw that for you. Okay, let's draw that quickly. And as long as you can understand it at this level, that's sufficient. Let's maybe draw the carbon oxygen pi bond here. Back into the plane of the page will be some R group, and then coming out at us is the nitrogen. And then there's another R group here. The pi bonding orbital between the carbon and the oxygen is above and below the plane defined by oxygen, carbon, and nitrogen. If the adjacent nitrogen is indeed sp2 hybridized, that would mean the lone pair would be in a p orbital. And you can see how that adjacent p orbital could participate in constructive interference without forming a node between the p orbital on nitrogen and the carbon-oxygen pi orbital. That involves electron delocalization, and that's stabilizing. Okay, so what did we learn about amides? Resonance is stabilizing. Resonance does not involve changes in geometry if the nitrogen in question, the blue nitrogen, is sp2 hybridized here, as it must be to participate in a pi bond. Then, by definition, it must also be sp2 hybridized here. The conclusion of that is that the lone pair must be in a p orbital, but that's okay, because being in a p orbital allows that lone pair to line up with the adjacent pi bond and to spread out in the way we've described for resonance. Yes?
So just to check, that left structure could be either sp2 or 3 if it was by itself, but because the right structure has to be sp2, that makes the left.
That's right. If you only knew about this and not resonance, saying that's sp3 is totally reasonable. But once you know about resonance and you see that the blue nitrogen is sp2 over here, it must therefore absolutely be sp2 here. Yeah. Follow-up question?
Could you show that to us on the example from the quiz?
Yeah, so can I show you that for the example on the quiz? That would have been this one. Good, yeah, so let's just do, I don't know, you want to do the one in the middle? Yeah, okay. So to get to the other resonance structure, I'm going to take these lone pairs. I'm going to use an arrow here, and I'll say more about the arrow that I just used. The arrow starts with the lone pair, and it points to where that lone pair is going. When it points to the space between two atoms, that means we're forming a bond, in this case a pi bond. Then I start the arrow with this pi bond, and I move it up onto the oxygen. That indicates that the pi bond between carbon and oxygen is breaking and moving onto the oxygen. I would draw a double-headed arrow to indicate that I'm writing a resonance structure. And then if it's okay, I'm going to call all of this R, and I will call all of this other R. And we would draw that other resonance structure like this. Oops, sorry, missed a little bit. And we would conclude, therefore, that the nitrogen must be sp2 hybridized in order for resonance to happen. Okay, other questions about that? Yes?
When you're looking at the double bonds, it doesn't matter which one is the sp2 line and which one is which one's the pi bond and which one is the...
Right, when I'm looking at a structure drawn this way, how can I tell which one is sigma or pi? It doesn't matter, you could start from either one. Just you need to know that one of them is sigma and lower in energy, and one of them is pi and higher in energy. Yeah? That's right. In order for resonance to occur, the nitrogen has to be sp3, 2. The reason for that is it's sp2 here, and in resonance we don't move atoms. So if it's sp2 here, it must also be sp2 in the first structure. Yeah?
So on a question, when you want us to draw the resonance structure, that's what you want and not the delta shown.
Right. When I ask you to draw a resonance structure, I want the double-headed arrow and at least one other structure, and not the hybrid. You can think about the hybrid. We'll sometimes draw the hybrid so you get the sense, but it's important that you actually draw the resonance structures, which is a perfect time for the next question on your quiz. So, for those of you playing at home or in class, here we go. Did I press record? Yeah, we're recording. You got two examples. One of them is pretty easy based on what you've already done. The other is a little bit more complicated. Start with the complicated one. I think this one you could probably get after the fact if we don't get to it today. So start with this one. And just to get you started in generating a resonance structure, look for lone pairs adjacent to pi bonds. You're going to use the arrows like we did on the other page. That is, you'll use a set of arrows starting with the lone pair to make a new pi bond, then you'll break another pi bond. Okay? Give that a try, see what you can do, and yeah, take maybe 2 minutes. how you doing? Need more time? Yeah, you got a minute? Good. Okay, you want to compare your answer with somebody nearby you, see what you got? Okay. Hopefully you've had a chance to discuss, maybe revise your hypothesis. Let me just point out why we're doing all of this stuff. When a child learns to walk, at least my experience with my kids is not that you sit them down as an 18 month old or however and give them a detailed PowerPoint presentation about how to actually move your feet and walk. They actually just start, and they start knocking into stuff and falling over, and parents just cheer them on. They have low stakes experiences trying to walk. It's not like you set them out on a tightrope and you say go to town. You give them a chance to fall on something that's not going to hurt, and eventually they get it. Same thing's true with chemistry. Your goal is not to learn everything so well that you never make a mistake. Your goal is to make as many mistakes as possible and then learn from them. So if you haven't made any mistakes so far, congratulate yourself, but your day will come, my friend, and it will come soon, perhaps in the next few minutes. All right, what is a resonance structure? Anybody feel like drawing? So we have a chance yet? Go ahead, come on now. Thank you for being brave. Your name is? Cambry. Okay. I really wish that they would brand Apple pencils to be more lightsaber-like. It would be cool. Somebody want to start a business? I'd pay for that. Okay, I think it's set on pencil, so go ahead and give it a shot.
Oh, that's kind of terrible, but.
Okay, good. I like it. How did you get to that resonance structure? Do you want to show us some arrows? If you did,
Oh,
you
yeah.
want to show us some arrows with the lone pair on that first structure to the left?
Yes. So I took these and moved them to here,
Okay.
and then wait. Am I confusing myself?
No, you're good. You're thinking your answer is missing something, but your brain is telling you this already. So see if you can fix it.
I feel like wait. Does the double bond go up to here instead of and then the double bond makes and then
If it went up
Wait.
to there, you'd have too many bonds to nitrogen. So where's the one place you could move that double bond? And just for context, let me thank you for being brave. It's hard to. No, stay there. You're not off the hook yet. This will teach you to raise your hand in class, right? All right, take a look at what we did there when we moved a lone pair and what we did with the pi bond. And we moved it out onto the adjacent atom.
Oh, yeah.
Okay, so does that, now see if based on that, you want to revise where this arrow should go. And you can use the eraser if you want to erase that arrow.
Oh, okay.
Great, then you can switch to the pen there.
So, the lone pair makes the double bond, and then the double bond goes to.
The other atom in the double bond.
So it goes to here?
Exactly.
Oh.
Okay, now, so you got to put in this structure, you got to put the lone pair on that carbon.
Oh, okay.
Now you got to.
And then it has a hydrogen right here.
Uh-huh, so what should its formal charge be?
It will be minus.
Good. All right, that was excellent. Thanks, Cambry, for being a good sport. That is exactly the kind of thing we were looking for here. We're looking for, I know how to get started, but then I don't know what to do next. Yes?
So to be adjacent, does it have to be like, you're talking about the bond adjacent to it, right?
Right, the three, we're talking about this is the atom that had the lone pair. This is the atom that is going to form the new pi bond. This is the other atom that was participating in the pi bond. And this was the key arrow that was confusing. This one was pretty easy to see as a first step, but then what do you do with the pi bond? And the point is, if you don't move the pi bond, you would have ended up with a structure that looked like this, and 5 bonds to carbon, that breaks the octet rule. And so you can't actually stop there. You have to move the electrons in the pi bond over, and they don't just disappear, they go out onto that atom as a lone pair. Now that was easier for you to see over here, probably where you already expected oxygens to have a lone pair. Yes, go ahead.
So it's possible for carbons to have lone pairs too?
Yes, it is.
I thought they just always had assumed hydrogens, and so I.
So it's possible for carbons to have lone pairs too. The assumed hydrogen you could have drawn in for the starting structure. I didn't because I am evil, but it was there. And when I do the resonance structure thing, resonance doesn't involve addition or subtraction of any atoms. The atoms all stay in one place. We move those electrons over to make a lone pair on that carbon. And you're seeing now a carbon with a lone pair on it is negatively charged. Yeah?
How does this work with formal charge? I thought we had used the formal charge the same resonance, but I might have just.
So we do have to keep the formal charge the same, but it doesn't have to be the same on each atom. It just needs to be the same overall. So we started neutral. Now we've got a plus on the nitrogen, but a negative on the carbon. And that would have been the other clue that the starting structure wasn't right, because you can't get a plus charge from nowhere. Yep, go ahead.
When you say overall, you mean the molecule?
Overall for the molecule, the sum of the formal charges has to be the same. Okay? Yes?
When you're drawing like the second one, do you have to draw all the carbons and hydrogens too? Because you added the hydrogen.
When you draw the second one, you can either choose to draw the hydrogens in or not. They will still be implied. My feeling is when you're first getting used to formal charge, it would be useful to draw in the hydrogens, at least on this carbon, because otherwise you might have a hard time telling that it's negatively charged. Yep. Great. So this is exciting because you've just learned something about this molecule. This molecule is called an enamine. And if you knew about bond polarity and electronegativity, you would say that the nitrogen's more electronegative than the carbon, and you'd expect the nitrogen to be electron rich, and it is. But resonance tells you that the lone pair on that nitrogen is also felt on that adjacent carbon. So you expect this adjacent carbon to be electron rich too. And we won't probably talk about that again this semester, but if you took a class in OChem, we would eventually get to the idea that enamines are reactive not only on the electron-rich nitrogen, but also on the adjacent carbon, and it's because of resonance. Okay, So that especially is going to take some practice. This one here is basically a version of the same one we did before with the Darth Vader and the Darth Tyrannus. Because this is hard, I will, when I upload a copy of this key, I'll give you a couple of bonus resonance problems for you to practice. And then problem 3 on your problem set is tough resonance problems that you should get started on. Make sure you can do it, okay? All right, any other questions about resonance? That's especially one you want to practice. Once you master it, it's not going to be a big deal. Until you master it, there's going to be challenges. You want to go ahead and make sure you make all the mistakes you're going to make right now. Okay, lastly, we still got like another hour together, right? Yeah. Don't you love that in sacrament meeting? No, this never happens in sacrament meeting. It sometimes happens in scientific talks. They're supposed to be 45 minutes, 50 minutes long. Somebody gets to like the 45 mark or the 47 mark, and then they say, and now switching gears, in the second half of my talk, I'd like to, and then they try to bust out 30 minutes of content in the last 5 minutes, which is what we're going to do today. No, actually, we're already pretty much all of the way there. We've learned about resonance. We've learned about formal charge. Now I want to return you to a concept that we talked about last time as we introduced the pi bond. Okay? And this is all of our stuff. I'm just going to copy and paste it wholesale as we remember the pi bond. And an important thing that I said yesterday about the pi bond is that the carbon-carbon pi bond is higher in energy than the sigma bond. Recall that the reason for that is that the electrons in the pi bond, because they come from p orbitals, once they form the pi bond, they hover above and below the plane that contains these nuclei. Each of these carbons is sp2 hybridized. It's trigonal planar. All of the carbons and hydrogens are in the same plane. The molecule is flat. The sigma bonds are all located in between the atoms. This is a carbon-carbon sigma bond. This is a carbon-hydrogen sigma bond. The electrons in those sigma bonds are in between the nuclei, close to the nuclei. The pi bond sandwiches that space between the two nuclei. It's not directly in between. It's further removed, and so it's higher in energy. That's really important because if we were to plot out the bond energies for the bonding and anti-bonding orbitals in this molecule ethylene, we would say, just keeping track of things, we would say that we have one carbon-carbon sigma bond. We have 4 carbon-hydrogen sigma bonds. That means we're also going to have one carbon-carbon sigma star antibonding orbital and 4 carbon-hydrogen sigma star antibonding orbitals. Then we have one carbon-carbon pi bond and therefore one carbon-carbon pi star antibonding orbital. Remember, we learned last time that for every bonding orbital in a molecule, for every bond in a molecule, there is a bonding orbital and an antibonding orbital. The bonding orbital is filled, and it's lower in energy than you would expect for an isolated electron on an atom. The antibonding orbital is empty, and it's higher in energy than you would expect for an isolated orbital on an atom. We're going to indicate that break-even point with the dotted gray line as we've done before, and this is just sort of the energy of an isolated electron on an atom, or the energy of an atomic orbital. So the sigma bonding orbitals, I'm not sure whether to tell you that the carbon-hydrogen bond is more or higher or lower in energy than the carbon-carbon sigma bond. They are different, but it turns out the distinction is small enough as to not matter at all in this class. So I'm going to say there are 4 carbon-hydrogen sigma bonding orbitals and a carbon-carbon sigma bonding orbital here. Their energies are not the same, but we don't care. They're close enough that we can consider them equal. Similarly, we would say that there are antibonding orbitals associated with those 4 carbon-hydrogen bonds, and then a carbon-carbon antibonding orbital. Again, they're not all the same in energy, but they're close enough to be similar, and this is sufficiently detailed for our purposes. Now, I told you that the pi bond was higher in energy than the sigma bond. So where in my energy diagram should I put the pi bonding orbital? Should we play warmer, colder? Should I put it above? Below the line, but where? Relative to the sigmas? Above. Because higher in energy means higher up in the energy diagram, means less stable, also means more reactive. So we expect the carbon-carbon pi bonding orbital to be higher in energy than the carbon-carbon sigma bonding orbitals. That's important. Similarly, what's above our break-even atomic orbital line is often a reflection of what's below it. So just as the carbon-carbon pi bonding orbital is higher in energy than the carbon-hydrogen and carbon-carbon sigma bonding orbitals, so the carbon-carbon pi star is lower in energy than the sigma bonding orbitals. The reason for that comes out of the MO theory math. You don't need to understand it for right now. Seeing what's above the line as a reflection of what's below the line is really all you need. And if you want to know more, you can come talk to me. Now that we've got the orbitals all accounted for, 1 bonding orbital for each bond, 1 antibonding orbital for each bond, and we have them in the correct energy, we can now fill these orbitals up with the available electrons. We have 2, 4, 6, 8, 10, 12 electrons, 12 valence electrons in ethylene. So 2 in each orbital, 2, 4, 6, 8, 10, 12. We see that the pi bond and the sigma bonding orbitals are filled, the antibonding orbitals are empty. Now, why are we doing this? It turns out knowing about the orbitals and their energies gives you potent predictive power, if you like being alliterative, for reactivity of molecules. You didn't know anything about ethylene before yesterday. Now you know enough to make an interesting prediction. If electrons in ethylene, let me back up. In organic chemistry, some molecules are going to be what we call Lewis bases. Have you ever heard of the term Lewis base before? Maybe you did in Gen Chem. If you did, you likely didn't understand it. A Lewis base is something that is an electron donor, but that doesn't mean it's like, hey, take my electrons and take them away. What it means is a Lewis base has a high energy pair of electrons that are reactive enough to be shared with another atom. We have another term for a Lewis base in organic chemistry, and that is nucleophile. What does that word mean? Well, phile comes from the Greek word for love, and nucleo reminds us of the nucleus. A nucleophile is a molecule that is anxious to share its electrons with another atom or nucleus. That's why it's a nucleus lover. Now, if a molecule were going to share its electrons with another atom, the ones to be shared should be the highest energy ones. Right? The most reactive electrons, the ones that want to change most, are the ones that are highest in energy or least stable. So, if ethylene were going to be a nucleophile, the most important electrons in ethylene that would be doing the chemistry would be these, the highest energy electrons. So you would already have a sense, even if you didn't know anything about reactivity of ethylene, if we were going to use ethylene in a reaction, you could already look at ethylene and say, I don't know what's going to happen, but I can tell you it's going to start with the pi bond. Because those are the most reactive electrons in the molecule. We call the most reactive electrons in the molecule the highest occupied molecular orbital. HOMO, HOMO, the highest occupied molecular orbital. Yes?
So if there was a lone pair, would that be higher than the pi bond?
Yes. If there was a lone pair, would that be higher in energy than the pi bond? Yes. So if you were going to be thinking about, and we can do another example of that, you will get to the point where you will look at the structure of a molecule like this, and you won't need to do the energy diagram analysis. You'll just remember sigma bonds are lower in energy than pi bonds. Therefore, the most reactive electrons in this molecule are the pi electrons. But let's do an example that's similar to the one you've just talked about. Let's do formaldehyde. Okay, we won't draw an energy diagram here. Well, maybe we will. Let's keep track of the bonds that are in formaldehyde. You have 2 carbon-hydrogen sigma bonds. You have 1 oxygen-carbon sigma bond. I have 1 oxygen-carbon pi bond. And then I have 2 lone pairs. Let's go ahead and do the energy diagram since we don't have that many to deal with. Here's our gray atomic orbital break-even point. E is for energy. Which are the most stable bonds in my molecule? Yeah, just the sigma bonds. And we're not going to make a distinction, even though there is a difference between a carbon-hydrogen versus a carbon-oxygen sigma bond. We're going to just assume they're all sort of close to the same. As I said, there is a difference. It doesn't matter for this class. Next should be what? What's next? Pi bond, and we're going to put it lower than the gray line. Why? Because it's a bonding orbital. That being in a bonding orbital is stabilizing relative to being not bonded. Now we have 2 lone pairs. Where are those going to go? Right on that line. They are not involved in bonds, so they're neither stabilized nor destabilized. Then the empty orbitals are going to be here, the carbon-oxygen pi star, and then the carbon-oxygen and carbon-hydrogen sigma stars. Again, we'll fill up the bonds with the available electrons, 2 bonds per carbon-hydrogen bond, sigma bond, 2 bonds per carbon-oxygen sigma bond, 2 electrons per carbon-oxygen pi bond, 2 electrons per lone pair. Now, look at that molecule. You tell me which are the most reactive electrons in this molecule. Lone pair. We would call the lone pair the highest occupied molecular orbital. There are 2 of them. They're equal in energy. That's fine. That happens a lot in molecules where you have 2 pairs of electrons that are equal in energy. So if formaldehyde were going to act as a nucleophile, what we care about is what the highest occupied molecular orbital is, and that is the lone pair on the oxygen. That means if the nucleophile were going to attack some atom, if formaldehyde were going to attack some atom to share its electrons with, the arrow would start with the lone pair on the oxygen. That's how you would start predicting what happens in the reaction. Okay? So that's if formaldehyde acts as a nucleophile. Now, we haven't talked about the concept of electrophile, but you can see that it's inverse to a nucleophile. An electrophile is a Lewis acid. An electrophile is a lover of electrons. An electrophile has, instead of a high energy filled orbital, an electrophile has a low energy empty orbital. that is willing to accept electrons. And when I say accept electrons, I don't mean like, here, have an extra electron. I mean share electrons from a nucleophile. In other words, we're starting to talk about what the thing is that the arrow is pointing towards. That's just the lecture prep, folks. Okay, and so for identifying an electrophile, what we care about is the lowest energy unoccupied molecular orbital. That is the antibonding orbital. That is the lowest energy place that a nucleophile would have to reach to share electrons to. You'll always go for the lowest energy empty orbital. Because like humans, electrons are lazy. They don't want to climb way up here if they can reach here. You're not lazy, I'm lazy. All right. So in formaldehyde, what is the LUMO? What is the lowest empty orbital? Yeah, that pi star. It's not the sigma stars. That should agree with what you know about pi bonds. Pi bonds are less strong. They are weaker than sigma bonds. So it follows that it ought to be, that the pi star should be lower in energy than a sigma star. Let's actually talk about what might happen if something with a high energy pair of electrons were to attack the pi star. But first, we need to draw what the pi star looks like. So I'm going to draw the carbon-oxygen the formaldehyde as though we're looking at it on its edge. This is a trigonal planar molecule. You've seen what a pi bond looks like. Scrolling up, that's what a pi bond looks like. The pi star for formaldehyde looks basically like you would expect if you drew two p orbitals side by side and you drew them with sort of a destructive interference with opposite wave function sign. In the pi star, there is a node in between the two nuclei, and that's common to all antibonding orbitals. The pi star is on both the carbon and the oxygen, and it's the antibonding orbital between carbon and oxygen. Now you can do the math of MO theory, and the math of MO theory tells you that the pi star is actually slightly bigger on carbon than it is on oxygen. That's not that important for what we want to talk about, but that's what the pi star looks like. That is an empty orbital. It's a waveform that an electron could adopt if it were at that energy level in this molecule. I'll just briefly, I really want to get to the punchline. So I will show you next time what a pi star looks like in 3 dimensions. But let's push forward a little bit. If this is the LUMO of a molecule, imagine I have over here a nucleophile, and we're not even worrying about what its structure is, but the nucleophile has a high energy pair of electrons that it wants to share by attacking an empty orbital on another atom. I'm going to start my arrow with the nucleophile. Where is the arrow going to go? It should attack the pi star. The pi star is both on carbon and oxygen. More of it's on carbon. So you might think, let's draw the arrow towards carbon, and you'd be right. The other thing that tells you that is that carbon is less electronegative than oxygen. So you expect oxygen, you expect the electrons in these pi and sigma bonds to be leaning towards the oxygen. You expect the carbon to be electron poor, to have a partial positive charge on it and a partial negative charge on the oxygen. So we would draw an arrow from the nucleophile's high energy electrons to the carbon. we're populating an antibonding orbital. We learned last time what that does. What does that do to the corresponding bond? Breaks it. Now, which direction is it going to break? And resonance should help you here. If I stop there, I'd have too many bonds to carbon. So what do I got to do? Push the electrons from the pi bond out onto the oxygen. And you, my friends, knowing almost nothing about organic chemistry, have just predicted a major way that molecules like formaldehyde react. And we will see that again and again and again and again. But it's all based on your understanding of high energy electrons on the nucleophile attack the low energy electrons on the electrophile. What happens next is predicted by the kind of empty orbital you attacked. I hope your brain is exploding. Okay, you need to go home and think about these things. On your quiz, go ahead and put your quizzes here. I will post the remaining problems on quiz 2, which require you to identify HOMO of a nucleophile and LUMO of an electrophile. Do that before you come next time.